So chapter 8 is about the periodic table, and it ties into the chapter, the concepts we learned about quantum numbers, the concepts we learned about electron configurations. And I gave you a handout here. We're going to go over this periodic table, but it virtually has every electron configuration of every element on it. Now, the way this periodic table works is it only shows the electron configuration of the electrons outside of the nearest noble gas. And let's look at the, before I even get started on the chapter, let's just take a look at an example of what I'm referring to here. If you wanted to write the electron configuration for silver, and silver is an atomic number, 47. Well, a silver is in the 1, 2, 3, 4, 5th period on the periodic table. And the nearest noble gas, you go up one period and to the right, is krypton. So you write krypton, the noble gas krypton, in brackets. The electron configuration is filled all the way up to krypton. And then the periodic table shows you the additional electrons above and beyond the filled shell for krypton. And it's right on the sheet here. You can see it's 4d10. So the 5 d orbitals in this 4th energy level is filled, and then it's 5s1. Okay. Now that is a little odd, but you might wonder what is going on here with silver, that there's only one electron in the 5s orbital when earlier in the period the 5s orbital got filled with strontium. Well, there's an unusual stability in all 5d orbitals having a pair of electrons, and it's at the expense of the 5s orbital. So for silver there, it's 5s1. And it is a bit of a glitch there, okay? But everyone see how we use the periodic table to determine, let's do another one here. Manganese. Okay, manganese, that's atomic number 25. And it's in the 4th period, and so we go up and to the right. Argon is the filled shell here, okay? And then for manganese, we have a 3d5 and 4s2. Now there's glitches in these transition metals that make it so that it's not straightforward in determining some of their electron configurations. You see trends as you go from left to right, and then all of a sudden the trend is disrupted. And that's why I'm just letting you work with this periodic table. The transition metals are really where the d orbitals come into play, and they give these metals their properties. But the first two groups, the alpine metals, the alpine earths, and then of course the last 6, the representative elements to some extent are straightforward. In the first two groups, alpine metals and alpine earths, we encounter new s orbitals as we go to the next energy level. And so we say that the s orbitals are filled there, and that's above and beyond a noble gas, of course. And then at this end of the periodic table, what gives the noble gases their unusual stability is this is where p orbitals are being filled. And you'll notice if you look at the noble gases, except for helium, of course, neon, argon, krypton, xenon, radon, all have filled p orbitals. For neon, 2p6. For argon, 3p6. For krypton, 4p6. And so again, it's something about filling the 3p orbitals for the new energy level that makes the noble gases so stable. So it's not the d orbitals that determine that unusual stability, it's the p orbitals. Well, we'll come back to this periodic table, but again, it has everything you need. We're using the abbreviation, of course, of having the filled shell up to the noble gas. The periodic table shows you those additional electrons, which are referred to as valence electrons for the main group elements. But these additional electrons above and beyond the filled noble gas, you can determine the electron configuration for any element on the periodic table with this piece of paper. The chapter on the periodic table, interestingly, at one time when Mendeleev, the Russian chemist, proposed the concept of a periodic table to organize elements according to their properties, and the elements that had similar properties were in columns or groups. At the time of Mendeleev, there was a lot of holes in the periodic table, but that gave chemists a heads up that there were some elements that probably hadn't been discovered yet. Well, we pretty much filled all those holes, and this is kind of interesting as far as the history of chemistry is concerned. Some elements, like gold, we've known about since ancient times. Some elements in these ones that are in tan here, above 103 atomic number, these by and large are elements that have just been discovered since 1965. Some of them are not stable for any length of time. They're synthetic elements. And then everything in between. So elements were discovered at different points in the history of science here. And generally speaking, we learned about s orbitals, p orbitals, and d orbitals, and f orbitals somewhat in the previous chapter. But generally speaking, group 1A on the periodic table, the outermost electrons in an s orbital. For alkaline earths, there are 2 electrons in the s orbital. D orbitals, by and large, are filled in the transition metals here. When you get to the main group elements on the right, now we encounter new p orbitals that are filled. And again, the distinguishing feature for the noble gas, except for helium, of course, is the fact that all 6 electrons have filled the 3p orbitals with that new energy level. And then the lanthanides and actinides, we're not going to talk about those much, but this is where we encounter the f orbitals, and they're right in this slit here in the periodic table. And they're at the bottom of the periodic table I gave you. This is kind of really a review, I think, of the beginning of the semester. But what we call the representative or main group elements are the first 2 groups, the alkali metals and alkaline earths, group 1A and 2A, and then group 3A through 7A. Of course, 8A is the noble gases. We've got transition metals here in blue. We've got our lanthanides and actinides down here. Because of, well, certain factors, they distinguish zinc, cadmium, mercury separate from the other transition metals. But this is really some concepts we might have talked about at the beginning of the class, at the beginning of the semester. Now, what about ions? Well, for main group elements, determining electron configuration of ions is very easy because you just get rid of the valence electrons. And let's just take an example here of magnesium. Magnesium on your periodic table is atomic number 12. Let's pretend we have a magnesium atom. Well, its electron configuration is 1s2, 2s2, 2p6. That's, so far that's 10 electrons, and then 3s2. That's its full electron configuration. Or we simply can group these together as neon, 3s2. And here you see the electrons above and beyond the filled shells. These are the valence electrons. These two electrons are the valence electrons. We've talked about that before. In the main group elements, or representative elements, the group number 1A, 2A, 3A, 7A, they tell you how many valence electrons there are. Okay? Well, obviously magnesium's in group 2A, it's got 2 valence electrons. It's very easy to determine the electron configuration for the most stable ion that's formed by magnesium if it loses those 2 valence electrons. Well, now it will have the same electron configuration as the neon atom. So when magnesium has a 2+ charge, its electron configuration is simply the same as neon, which is this, of course. Okay? Easy. This is really what's considered the driving force for why main group elements form the ions that they do. They end up having the same stable electron configuration as a noble gas. The nucleus, of course, is still the same. Magnesium hasn't turned into a neon atom. Of course, that's nonsense. But the electron configuration is the same as neon atom. When an ion and an atom have the same electron configuration, we say they're isoelectronic. Okay, so that's a term you want to be comfortable with, isoelectronic. Now we can extend this on both sides of neon. We've talked before about, for the representative elements, what ions they're most likely to form. And so let's say we write neon here, and for fluorine, it tends to gain 1 electron and form fluoride. We've talked about this before. For oxygen, it tends to gain 2 electrons and form oxide. For nitrogen, it tends to gain 3 electrons and have a 3- charge. So those are anions that are going to be isoelectronic with neon, and then going the other direction. If sodium loses an electron, it ends up with a + charge. We just mentioned magnesium. If it loses 2 electrons, now we'll have a 2+ charge. And then aluminum, and we'll stop here, if it loses 3 electrons, it has a 3+ charge. And all of these species here have the same electron configuration. They're all isoelectronic. They all have the same electron configuration as a neon atom, which of course is 1s2, 2s2, 2p6. Okay? So if nitrogen loses 3, nitrogen gains 3 electrons. And if you want, just for convenience, we can put their electron configurations on the left here before they either gain or lose electrons. Neon, again, is 1s2, 2s2, 2p6. So sodium's going to have one more than that, 1s2, 2s2, 2p6, and its valence electron is 3s1. For magnesium, 1s2, 2s2, 2p6, 3s2. For aluminum, now we need to start using a p orbital. 1s2, 2s2, 2p6, 3s2, and 3p1. Going the other direction here, fluorine gains an electron to form fluoride. It starts out 1s2, 2s2, 2p5. Oxygen, 1s2, 2s2, 2p4. Nitrogen, 1s2, 2s2, 2p3. So here, with these nonmetals gaining electrons, and with these metals losing electrons, they're all trying to end up with the same electron configuration as a neon atom. Okay? Everybody see how that works? So the main group elements or representative elements that have predictable charges for the ions they form, the driving force is to end up with an ion that has the same electron configuration as a noble gas. Okay? Well, here it shows you some other examples, I guess. Actually, most of these are the same. Sodium atom, it loses one electron, has a +1 charge, it has electron configuration same as neon. Calcium, its electron configuration is argon 4s2. If it loses 2 electrons, it's going to have the same electron configuration as the noble gas argon. Aluminum loses 3 electrons. Hydrogen, and even an example of this, if hydrogen gains 1 electron, it has the same electron configuration as the noble gas helium, and indeed, chemists, we have made a number of compounds that have hydrogen with a negative charge. That ion is called hydride. We've made sodium hydride and other compounds where the hydrogen atom has gained an electron and actually formed an anion. We already mentioned fluorine, oxygen, and nitrogen on the board here. Also, for representative elements, we mentioned this near the beginning of the semester, the charges of the ions they form is quasi-predictable. Group 1A, these alkali metals, form ions with a +1 charge because they lost an electron. The alkyl earths, a +2 charge. The halogens, -1. Oxygen, sulfur, -2. Nitrogen, phosphorus, -3. And then for aluminum, +3. Okay? So again, here it's defining this term we mentioned before. If an ion and an atom, or 2 different ions, are isoelectronic, all that means is they have the same electron configuration. And what I drew on the board here, all these ions and the neon atom are all isoelectronic. They all have the same number of electrons, and they all have the same electron configuration. Okay, does that make sense? Now, transition metals, there won't be any questions on the exam about ions that are formed by transition metals. I think earlier we mentioned that there's really no easy rules for predicting what ions are formed by the transition metals. And some of the transition metals form more than one cation. That's why we need the stock system to name those compounds, because copper can form an ion with a +1 charge, copper can form another ion with a +2 charge. Iron can form an ion with a +2 charge. Iron can also form an ion with a +3 charge, and so on. And the electron configurations follow a slightly different format. If you might see this on a homework problem, but it won't be on the exam. But let's read. When a cation is formed from an atom of a transition metal, electrons are always removed first from the s orbital and then from the d orbital. And of course, we're talking about the outermost s and d orbitals. So let's look at this example with iron. This is the electron configuration of an iron atom, and it should be the same, hopefully, on the periodic table I gave you, 3d6,4s2, good. This is the electron configuration of iron. Its argon is the filled shells, and then 4s2, 3d6. Well, when it forms an ion with a +2 charge, it loses these s orbital electrons first here. And it still has 6 in the d orbitals. Or we can just write it argon 3d6. On the other hand, when iron forms an ion with a +3 charge, again it loses those 2 electrons that are in the s orbital, 4s orbital, and also it loses 1 electron from the d orbital. So it's a little different for transition metals. Again, there's no questions on the test about those ions. The chapter also talks about effective nuclear charge, and this has to do with the positive charge that's felt by an electron. Now, why would the charge that's felt by an electron be any different than the actual charge of the nucleus? Well, we've been learning about these orbitals, and so if you're in an electron in an outer orbital, or valence electron or something, the protons are in the nucleus, but then there's layers of electrons in the filled orbitals before you get to the outermost electron. That affects what the positive charge is that the outer electrons are experiencing. And so that's what the term means, effective nuclear charge. And since the positive charge that's felt by the outermost electrons is less than the charge in the nucleus, we say that some of that positive charge is shielded because of the other electrons in the inner orbitals that are between them. Okay? Now this will affect the radius of atoms. One thing, as you move from left to right across a periodic table, interestingly I suppose, but don't forget when you're moving from left to right across the periodic table, you're adding one more proton in the nucleus for each of these elements. The effective nuclear charge is kind of going up because all the filled shells are about the same, and what happens is the size of the atoms actually diminishes. The radius gets smaller. These orbitals are pulled in because the positive charge is increasing one proton at a time. So generally speaking, and they have ways with X-ray diffraction and other techniques to determine the dimension of atoms and molecules. And it's experimentally confirmed that as you move from the left to right on the periodic table, the size of the atoms actually gets smaller. The positive charge is increasing in the middle. It's pulling in all the shells as a result. And this is related somewhat to this concept. Okay? And here you can see this. If you start with sodium, and this is probably in angstroms. I think I owe you a definition of that. A lot of times, for convenience, when we're talking about the dimension of atoms and molecules and bond lengths, a lot of times we use this unit called angstroms. 1 picometer is 0.01 angstroms. Let's do it the other way, so it would be, so 1 angstrom is 100 picometers. And angstroms used, part of the reason angstroms used is it's convenient. You can see the radius of a sodium atom is 186 angstroms. It's just a convenient unit to use. It's kind of between picometer and nanometer. But more importantly, as you go from left to right, sodium, magnesium, aluminum, silicon, phosphorus, the size of the atoms is getting smaller. You're adding another proton. You're adding more protons to these elements as you move from left to right. That's just a periodic trend. Now, if you go down a group, of course, you're adding more electrons and the atoms get bigger this way. So as we go down a group, the size of the atoms increases. We've got more shells, more electrons. But when we go from left to right, we're only adding 1 electron at a time, and we're adding a proton in the nucleus that pulls the orbitals in. And here you see the trend for the periodicity on the periodic table as you go from sodium to chlorine, which is on 1 row or period, as you go from potassium to bromine, as you go from rubidium to iodine. You see, with some glitches, but you see, generally speaking, the size of the atoms gets smaller as you go from alkali metal to halogen. Now, here, this is going to be intuitive. If we have an atom and we take electrons from the outer orbital, we expect the ion to be smaller, and it is. Here's an example: lithium, sodium, potassium. If you remove the valence electron, now their radius, and this time it's in picometers, is smaller. You're removing outer electrons. The atom gets, when it forms a cation, gets smaller. On the other hand, if you have an atom and you add electrons to form an anion, well, now you're adding electrons to outer orbitals and you're making the ion bigger. And so as we go from halogen atoms to halogen anions, the radius increases. And here you can see when a lithium atom reacts with a fluorine atom to make lithium fluoride, the lithium ion gets smaller than the lithium atom was, and the fluoride ion gets bigger than the fluorine atom was. Cations are always smaller than the atom, anions always larger. And here it shows you the dimensions of cations and anions. Another periodic property on the periodic table is ionization energy, and to determine ionization energy, it's the energy, the voltage required for an atom of an element to lose an electron and conduct an electric current. They need to fill a tube with the element in the gas phase, and then they apply electrodes to it and they measure what voltage is required to cause the atoms to ionize. And it's quasi-predictable which elements you think are the most stable, and so they're going to take the most voltage to ionize.
Noble gases.
The noble gases, good. So their ionization energies are very high. They're very stable atoms compared to the other elements in the periodic table. And then elements that tend to lose electrons more easily, like the alkali metals, sodium and potassium, their ionization energy is much lower. They really want to lose some electrons, so to speak, to form a cation. And then the other elements are sort of in between. And then also they can determine second and third ionization energies. and these are higher still. It takes even more energy to remove a second or third electron from an atom than the energy it takes for the first one. And this table just shows the experimentally determined ionization energy for the first 20 elements. But here is a nice graph that shows, based on the position in the periodic table and relative to elements near it. Notice that the most difficult elements at the top of these peaks are all noble gases. So it's more difficult, it takes more energy to ionize helium than it does hydrogen or lithium. It takes more energy to ionize neon than the elements on either side of it on the periodic table. It takes more energy to ionize argon than other nearby elements. And then at the bottom, notice you have here the alkali metals that are easiest to ionize. Lithium, sodium, potassium. These take much less energy, much less voltage, to ionize than other nearby elements. So this is a periodic trend that's kind of predictable based on what we know about those elements. And we're going to skim over most of this chapter here today. There's another parameter that can be measured called electron affinity. It's the energy required for an atom to gain an electron. And graphically, we expect the halogens to have very high electron affinity, and they do. Fluorine, chlorine, bromine, iodine very much want to form an anion with a -1 charge. And so they have much more electron affinity than other elements on the periodic table. Okay? Now then the rest of this chapter kind of just discusses the general properties of each group based on what we learned about involving electron configurations. I mean, group 1A, the alkali metals, they have one valence electron. It's in an s orbital. And these tend to be very reactive metals. These metals don't exist in nature as atoms. They exist in nature as ions with a +1 charge, like sodium and potassium. In fact, sodium and potassium ion are actually electrolytes in our blood plasma. Okay? The way we find alkali metals in nature is as ions with a +1 charge. If we want to study the element, we have to make it. We have to make atoms starting with the ions. But when you do have these metals, they are very reactive. And so are the alkaline earths, magnesium, calcium. They have 2 valence electrons in an s orbital. When you get to 3A, of course, you have one of the elements you have is aluminum, and it has 2 electrons in a new s orbital and then 1 electron in a p orbital. And this is spelled out right on your periodic table. If you look at group 3A on your periodic table, all those electron configurations have 2s2 and 2p1. And then when we encounter the d orbitals, they're all filled. When we get to gallium, atomic number 31, well, we have 4s2, 4p1, and then the 3d orbitals are filled. There's 5 of them. They each have 2 electrons, 3d10. But the outermost electrons for those elements is thought of being the s and p orbitals that are new for that period on the periodic table. And so we're not going to go into this in too much detail, but these electron configurations, and most specifically, the outermost electrons and the valence electrons determine the chemistry of these elements. So I'm going to kind of skip over these. This one is the halogens. I mean, they have 2 electrons in an s orbital and then 5 electrons in a p orbital that consist of the 7 valence electrons they have. Here are the elements: chlorine's a gas. So bromine is actually a liquid, but here's some of its vapor, and iodine is a solid. But these are the halogens. We mentioned this before, but the reason that the noble gases in nature generally don't form compounds is they're so stable. When they have 2 electrons in an s orbital and 6 electrons in the p orbital, and so both of those are filled, this constitutes what appears to be the unusual stability that the noble gases have. One thing about noble gases, they have very high ionization energies, but that doesn't mean we don't ionize them all the time, because if you've ever heard of a neon sign, well, they take a tube and fill it with neon gas, and they apply a very, very high voltage. And here you can see this is actually neon right here. This is kind of the color you usually think of for neon signs. It's kind of red-orange. This is the light that's given off when neon ionizes and conducts an electric current at very high voltage. But some neon signs might not be neon signs at all, because here's a helium, ionized helium, here's argon, here's krypton, xenon. They have different colors they give off when they ionize. So even though noble gases, you have to really crank up the voltage to get them to ionize. Once they do, they give off different colors of light. Actually, it's a different blend of wavelengths. Okay. But they're all difficult to ionize, and then when you turn off the voltage source, they just go back to being atoms. Okay? They don't form anything new. One thing, even though in nature, generally speaking, the noble gases, we don't find them in compounds much or at all or whatever, but we have made derivatives in the lab of xenon and krypton. So it's possible to make compounds. But by and large, the noble gases are so stable, they exist in nature as atoms. I'm going to skip through this, and I think that's really all there is to this chapter. Now, let's look at the study guide. As far as for chapter 8, most of this is pretty straightforward, and some of it really we discussed at the beginning of the semester. Can you remember what the group name is for the main group elements in 1A? Alkali metals. What about 2A?
Alkaline earth metals.
Okay, alkaline earths. 7A?
Halogens.
Halogens. What about 8A?
Noble gases.
The noble gas. Okay. Yeah, well, you kind of have to know. It's hard to miss where the transition metals are on the periodic table. Electron configuration of elements on the periodic table, and I'm giving you this handout. It says figure 8.1, but this is what you need to be able to work with. Also, the valence electrons for the representative elements is the same as the group number, isn't it? For group 1A, there's 1 valence electron. The number that precedes the letter A, it tells you how many valence electrons those elements have, right? Also, charges of ions formed by the representative elements. I think we went over this at the beginning of the semester, but you'll want to know it again for this exam. What charge ions do the alkali metals have? +1. What about the alkaline earths?
+2.
+2. What about the halogens? You take the group number -8, 7 -8, -1. What about oxygen? -2, and nitrogen? -3, okay. We now know what isoelectronic means. And really, above and beyond electronic configurations, if an ion and an atom have the same number of electrons, they're gonna be isoelectronic. They're gonna have for our purposes, they're gonna have the same number of electrons, and if it's a main group element, the same number on the same electron configuration. Now, that theory kind of broke down in the transition metals. When transition metals form ions, electron configuration is not necessarily isoelectronic. But there's no question on the exam about the ions of transition metals. So for the main group representative elements, if they gain or lose electrons, the electron configuration is the same as an atom of the nearest noble gas, usually. Make sense? Isoelectronic means they have the same number of electrons. If it's a main group element, they have the same electron configuration. Trans and atomic radii, we said we go down a group, the radius of the atoms gets bigger. If we go across a period, the radius of the atoms gets smaller. Trans and first ionization energy as well. The elements that are most difficult to ionize are noble gases. The ones that are easiest to ionize are alkali metals. Okay, good. All right, so that's pretty straightforward. Let's do it before we take a break. This is going to be quick. At least these are pretty easy. 7. What's the electron configuration of a calcium atom? Well, just look at your sheet for calcium. It's argon and then 4s2.
Sir?
Yes?
She didn't have one of these papers. She came in late.
Oh, here, I'm so sorry. Does everyone see for calcium, it's argon in brackets 4s2?
Yes.
Any question about that? Okay, I'm looking at the number 7 of the practice problems. Calcium electron configuration is argon in brackets 4s2. What about a calcium ion with a 2+ charge?
Would it just be argon?
It'd just be argon. It's isoelectronic with an argon atom. So calcium with a 2+ charge, its electron configuration is argon in brackets. Oxygen atom,
Oxygen?
helium in brackets.
2s2, 2p4.
Okay, 2s2, 2p4. Just
Yeah.
like taking candy from a baby. Oxide,
Would be helium 2p4? Or just helium?
it'd be neon. It's helium 2s2, 2p6, which is neon. Does everybody see that?
How does that happen? How do you
If
get
oxygen, which has 8 electrons, gains 2 more and has a 2- charge, now it has 10.
that?
Puts you at neon.
That puts you at neon. Does everybody see the
Just
elect?
neon on brackets?
Just neon in brackets? I mean, it wouldn't be wrong if you put 1s2, 2s2, 2p6, but if you want to save ink, it's neon in brackets. What about a hydrogen atom?
1s1?
Good. What about hydride?
Helium?
Helium in brackets or 1s2, either one. A lead atom,
I know, of course.
it's atomic number 82.
Okay.
To be, xenon?
Xenon in brackets,
And 4d10.
4f, 14, I'm sorry.
4D10, 5S2, 5P6.
It's right with, yeah, exactly what you see there. And for lead, it's xenon in brackets, 4F14, 5D10, 6S2, 6P2. Do you like this periodic table or what?
Yeah.
Would you rather figure these out from scratch?
No.
Okay. What is the charge on a monatomic ion of sulfur? What anion does sulfur form?
I'm sorry,
Organic chemistry too.
What charge is sulfide?
Negative.
Okay, -2 or 2 minus. Nitride,
A negative,
Negative 3.
-3 or 3 minus. Oxide,
-2,
-2 or 2 minus. Fluoride,
-1.
-1. So this is pretty easy, the last two problems, all right? All right, let's take a break. We're gonna do the quiz and then we're gonna do half lab.